This is David Spears, instructor in civil engineering at Texas Tech University, talking about CE 2301 statics. This is about directed force vectors and dot products. First, directed force vectors are used for cables. First, we determine the position vector for the cable by knowing its endpoints. Then we get a unit vector for the position vector. So it's easiest to show it on an example. If I have a cable secured at one end to point A, which is at coordinates 3, 4, and 0, and the other end of the cable is connected to this point B at 0, 0, 12, and I know that the force in the cable is 325 pounds, then I can draw up and show a position vector RBA, that's tip over tail, by just taking the coordinates of the tip and subtracting from it the coordinates of the tail. So 0 minus 3I, 0 minus 4J, plus 12 minus 0K. Units are feet. So that means my position vector RBA is equal to negative 3I minus 4J plus 12K. I can figure out the distance from point A to point B as just the scalar magnitude of this, which is a square root of the sum of the squares, 13 feet. And then I can write a little position vector, which is length of 1, in the direction of the vector F. So that's just the position vector RB over A divided by the magnitude of RB over A. So it's these. Express the vector as this, negative 3, negative 4, plus 12, divided by 13. My unit vector looks like this, negative 3/13 I minus 4/13 J plus 12/13 K. And finally, I can express my vector F as scalar F times the unit vector UF. So it's the scalar is 325. Here's the unit vector. Multiply it all out. Negative 75I minus 100J plus 300K pounds. We're going to use that work backwards a lot to solve for the force in a cable. And we'll see that as we go on through the semester. The second concept, really important concept, is called the dot product. We show it by a dot between these two vectors. The dot product is used for projections of one vector on another and to determine the angle between vectors in 3 dimensions. Very important. So I show these two vectors A and B with an angle theta between them. Dot product is defined as vector A dot vector B is equal to the scalar magnitudes of those two vectors times the cosine of the angle between them. That is a scalar, just a number. The properties of it are, it doesn't matter their order. A dot B is equal to B dot A, it's commutative. A dot B plus C is equal to A dot B plus A dot C. It's distributive. Okay, to look at the math of these things, I want to go back to the unit vectors of these, the main vectors that we're doing the dot product of. Because the cosine of the angle 0 is 1, then looking at unit vectors, I dot I is equal to 1, as is J dot J and K dot K. Similarly, but opposite, because the cosine of 90 degrees is equal to 0, I dot J is perpendicular to each other. I and j are perpendicular to each other. So I dot j is equal to 0. Similarly, I dot k is 0, j dot k is 0. Because they're perpendicular. Because of the commutative law, I can reverse that. J dot I is equal to 0. So, if I take these two vectors, A and B, and express them in their Cartesian format like this, AXI, AYJ, AZK, do the same thing for B, and then I do A dot B, that is going to be equal to the AX term times the BX term, and because of this distributive property, it's I dot I. Well, that goes to 1, and I dot I is 1. AX times the scalar magnitude AX times BY. Then I have the I dot J. Well, that goes to 0. Because of this, they're 90 degrees to each other. The cosine of 90 is 0. Similarly, AXBZ goes to 0. AYBX goes to 0. Perpendicular. AYBY are both J dot J, so that goes to 1. AYBZ goes to 0. AZBX, those are perpendicular, goes to 0. AZBY, perpendicular, goes to 0. AZBZ, parallel, K dot K, goes to 1. So I can eliminate all my zeros, and I'm left with A dot B is equal to AX times BX plus AYBY plus AZ times BZ. That's just a scalar number. Just multiply those two numbers, those two numbers, those two numbers, add them all up. And because of this relationship up here that I started with, A dot B is equal to A scalar B times scalar B cosine theta, I can rearrange that, and I can say the cosine of theta, the angle between them, is equal to AXBX plus AYBY plus AZBZ divided by the magnitude of A times the magnitude of B. I'm going to use this to find the angle between two vectors, a very useful function. Here's an example, simple example. One way of using this is I'm given two vectors in their Cartesian formats. F1 is 3i minus 12j plus 6k. F2 is negative 2i, 3j, and 16k. I first do the square root of the sum of the squares to get the magnitude of F1, 13.75 pounds. F2, the magnitude, is the square root of the sum of the squares, 16.4 pounds. So F1 dot F2, I just multiply the x terms times each other, 3 times negative 2, plus negative 12 times 3, plus 6 times 16. Do all the math. That's negative 6, that's negative 36, and that's what? 96. Works out to be 54 pounds. That is also equal to, from this relationship up here, F1 scalar times F2 scalar times the cosine theta. I can rearrange that and solve for the cosine of theta is equal to F1 dot F2, which I just saw was 54 pounds, divided by F1 scalar magnitude times scalar of F2, 13.75 times 16.4 is equal to this number, and I can do the cosine inverse of that number to get what theta, the angle between them, is 76.1 degrees.